I want to show you guys real quickly how to get the data in here. And what I'm going to do, I'm just going to real quickly do what you can see here on the left. Obviously, it won't give you the same numbers as what you should have gotten for the practice, but it'll at least give you guys an idea of how you can get the data in, and actually how you can even get box plots and things as well on your calculator. All right, so starting out, you're going to want to go to Stat, and then number one is Edit, and it'll give you empty lists, okay? Or if you happen to have something in the lists, it'll give you that. And in fact, if you go to Stat and hit number 4 first, it'll clear out all the data that might have been in your lists first, okay? But we'll go to Edit, and I'm just going to type these in here, 103, 96, 113, 111, and 126, 111, 87, 90, 121, 99, 87, 127, 117, 131, and 115, okay? So we've got all of those. That's all the old type of this light bulb that they're testing, or at least the ones we're going to look at. And then you have the new type, 146, 131, 132, 160, 128, 191, 117, 132, 107, 141, 133, 124, 153, 129, and 118. Okay, so we've got those in here, and now we want to do something with it. So I'm going to first of all hit quit to get out of there, and then there's a couple of things here. First of all, if we go to Stat and Calculate, we have our one variable statistics, okay? Now, we're going to do one variable statistics on the data from list 1. Now, obviously, these won't be the numbers that you get if you had all the data for the old type, but notice it gives us our mean, and then it also gives us the sum of all the scores, the sum of all the scores squared. We have the standard deviation, which we'll talk about later. It gives you n equals 15. I typed in 15 of the scores. That's a sigma, that's standard deviation. And then it actually will give you your 5-number summary down here at the bottom. Okay? Now, for tomorrow, you are going to need to be able to calculate, find your 5-number summary on your own. But in the future, you'll only be allowed to use your calculators for arithmetic for tomorrow. In the future, though, if you're asked and it's on a calculator portion, you can get those numbers real fast with this, okay? Now, you could do this with both sets of data. The other thing I want to show you, though, is if you hit second y equals for stat plot, I'm going to hit enter on plot number 1 and turn it on. And then notice the type. Right here is a scatter plot. For a scatter plot, you have to have 2 lists of data. So you've got to have your x coordinates and your y coordinates. Okay? We're not going to do a scatter plot. We're going to do a box and whisker plot. Now, notice it has 2 different kinds here. The first one on the left here will actually give you identify outliers. Okay? So I'm going to choose that one. Notice it's looking at the data in list 1. And then the other thing I'm going to do is you need to make sure your window is set so that you can actually see it. Now you don't need to really worry about the Y, but the X Notice our lowest one is 87, our highest one is, well, in this one it's 191. So I'm going to go from 0 to 200, just so I have a good thing. So I'm going to go to Window, set my X min at 0, my X max at 200, and now I'll hit Graph, and there's the box and whisker plot for at least a portion of the data that I typed in for the old type. Okay? Then we could do second, go back to stat plot, turn the second one on, and tell it to do a box and whisker plot with list 2. With our other data, now when I graph it, I've got both of them, and you can see we can do a side-by-side comparison. Actually, if you hit trace, there's your min, quartile 1, median, quartile 3, max. And then if you hit the up or down arrow, it'll switch to the other graph. There's the max at 191, but it identifies it as an outlier. So the end of the whisker is at 160, third quartile is 146, median 132, first quartile 124, and your min is at 107. Okay? Now, if you had typed in all of the data and done that, you actually would have gotten this. Okay? So here's all of the data for both of those with all of the data they gave us in it. Okay? Now, let's start answering some of the questions here and looking at the situation. Manufacturer of light globes, or light bulbs, claims that their new design has a 20% longer life than those they are presently selling. 40 of each globe are randomly selected and tested. Here are the results to the nearest hour. So, first question, is the variable discrete or continuous? Discrete. Okay, Michael's saying discrete. What do you guys think?
Continuous. You cannot wait. Oh, to the nearest hour. So, continuous. Because you can't, it's rounded. So
That's why it's discrete.
So, it's rounded, so that's why it's discrete.
discrete is like,
Discrete means we have distinct values that are completely separate.
Yeah, sorry.
Continuous would be like if we timed it down to the second or whatever, and then we'd have to deal with kind of ranges. Here are the ones that are. Yeah, that's okay. That's okay. You're participating, and that's good. So, all right. So this is discrete. We've rounded it, so we have these unique values that are separated. Part C, the first part of that is kind of easy now that we've done the box plots. Yes, there is an outlier, that 191 in the new type. Okay? The question is, should it be deleted?
How can you tell? Like
If it's an outlier?
if an outlier is just like something that's like obscure and like far away from all the
Well,
data, how can you tell if it's far enough?
We actually defined that on Friday. We have the IQR. We have the IQR, which is between Q3 and Q1.
Okay, so outlier.
And it's 1.5 times the IQR away from, in this case, it would be above Q3. All right? So Q3 is 143. Q1 is 124.5. So that's 19.5.
That's the IQR.
Or 18.5, I'm sorry. The IQR would be 18.5.
So that's 27.75.
Yeah, that's our IQR.
So if the outlier is above 27.75.
27.75 beyond 143. Plus 27.75. That gives us 170.75. Okay? Now, as we look through this data, none of the other values are beyond 170.75. Okay, so this one right here is the outlier. All right, and by the way, the whisker then would be drawn to the next highest one, which it looks like is 164. Is there another higher one? There's a 160. Yeah, so the whisker here is drawn to the next highest value that's not an outlier.
So,
Okay, so here's 164 right there.
can it be, if it's greater than or equal to 1.5 times the IQR plus Q3, it's an outlier?
It has to be greater than.
Okay,
Like
but
if
it
we
can
had
be-
one of our values that was 170.75, that would be okay. It's beyond that.
Okay.
Okay, good question. All right, so here's the question. Should we eliminate this value, 191, from our data? And then like reanalyze everything.
I mean, if I were doing an actual study and found an outlier like that, I would investigate to see why that outlier happened in that particular test. If I couldn't find an answer why I analyzed the data with it and without it,
Okay, not a bad strategy. What do you guys think?
If it was something important, then yes, but because it's life bombs, then no.
So it depends
Like,
on
if it was
whether
a-
you feel like the data is significant.
Yeah, like if it was medicine, I obviously wouldn't be like, that outlier is not important because that's a person, but who cares about life bomb? It's more IB thinking. Like, I don't.
So we don't care if light bulbs die, but if it's a person that can die, then we should
Yes.
probably do something about that.
Yes, that is. Yeah.
Well, let me give you kind of the rule that we should follow. Okay. Unless there is something that went wrong with the process, you should keep the data in there. Okay. I gave the illustration this morning about, let's say we went out to the track and we had everyone run 100 meters, okay? And we were going to we timed everybody to see what the times for finishing 100 meters were, okay? If there was somebody who, completely tripped and fell halfway through the race, and then got up, brushed himself off, and staggered to the finish, okay, that would clearly be an outlier, because it took them forever. That would be an outlier that we would want to eliminate, because there was a problem with the process, okay? They fell. Now, if it was just someone who's really, really slow, and it takes them 20 seconds to finish the 100 meters or 25 seconds to finish 100 meters, okay, we would still keep that data point, okay, because there was nothing illegitimate that went on there, okay? It's just there was someone who was really slow. And that applies with anything. If it's not the result of some kind of mistake, maybe in the process or measuring or something like that, you keep the data in there, okay? Because it all is a part of it. So, now I want to look at part of why I wanted to go over this problem anyways is to take a look at side-by-side box plots, okay? We can draw some conclusions and make some comparisons based on the box plots that actually are kind of helpful compared to just looking at numbers, okay? What are some things you see when you look at the box plots here?
That one, the one on top has like the thin side on the right.
Okay. What? Okay, the quartiles are different sizes. Do you mean from one to the other, or like within the same box plot?
From one to the other.
Okay. So like for this one, the bottom 25% is spread out a little bit more than the bottom 25% on this one. Okay. Here, this is spread out a little bit more than this one. Okay. Once you get up on the top end, this is a little closer. This is a little bit spread out more. And then the top 25%, that's actually not too much different. Maybe just a little bit. Okay? All right? It's a good observation. What else do you see? All right, I see. What do you see?
75% of the bottom data, or of both sets of data, like overlaps. Or something like the third to the max.
Okay.
And then the minimum to the
Is that what you're trying to show?
yeah.
Kind of, yeah, like the top 50% or a little bit more is contained in the bottom 50% of the newer bulbs. Okay? That's good. That speaks to their claim that they're 20% better. Okay? I'd say they're at least 20% better, probably. And in fact, if you compare all of these numbers, okay, this was like 26% better
How did you get
as a mean.
those percentages?
Hmm?
Like, because,
You mean the 20%?
yeah.
They were claiming that the new design is
No, I
20%
know, but
better.
like if we're trying to confirm that, and like Sarah said, like, there's an overlap, then do you just take the stuff that's not in the overlap with the bigger one? Of the
Well,
lower one?
you can't get an actual percent just by looking at the box plot. That we would get from the data here.
Could you just
Okay.
take the 20% of 107 is so you add them and say that?
Yeah, yeah. So like 20% of this, I think, was like something like 21 or whatever. And if you add 21, you're up to 128, when that's higher than 128.
It's 1.4.
Okay, so you can do that with all of those numbers there. Let's look at the box plots themselves. Okay, how would you describe the distribution for the old bulbs, the old design? How would you describe the distribution?
More on the lower 50%. With more data. It was
Okay, what about the lower 50% of that compared to the upper 50%? What were you going to say? Okay, the old one we could say is negatively skewed. Look at the bottom two quartiles. All right, see how much more spread out the bottom 50% is than the top 50%? Okay, that being spread out like that is what would make this negatively skewed. Now, what does that tell you about the design?
It's not good.
it's not probably.
Okay, how so? Like, if we're having a lot that are kind of short down here,
A lot of duds.
yeah, that design for some reason, while it did have a good 50% that were in a decent range up here, you had a lot that were, failing prematurely. Okay? a lot of defective bulbs. This is pretty symmetrical, okay? The two whiskers on either side are about the same length. I know the median isn't exactly in the middle here, but we don't have any, when you're looking at symmetry, it's not so much necessarily where the median is specifically, but it's, if you look at the whiskers themselves, even with this outlier, you know, it's not going to pull it too far one way or the other. So we would say this is pretty symmetric. Okay? Now, a symmetric kind of distribution tells us something about our new design. What would that tell us? We're not getting a whole lot of duds. We're not getting a whole lot that are extraordinary. They're all pretty normal, pretty consistent, right? This is a little more of a consistent design, okay? If we were finding like the standard deviation and whatnot, this would have a smaller standard deviation because it's grouped a little tighter, okay? So, not only are we getting a longer lifespan, we're going to have fewer duds, and we're going to have a little more consistent. It'll be a little more predictable, okay? So those are some things that you can tell when you're dealing with a side-by-side comparison. And one thing that I think is kind of telling too about these is, notice the max here is almost equal to the median of the second design. In fact, the max is just under the median of the new design. Okay? So even the old design at its best was just right in the middle of what the new design is capable of. Okay? So guys, this is the kind of thing that, you know, as people engineer and develop new products, this is the kind of stuff they do. All right? One of the questions is then, is this good enough to roll out a whole new product? You know, change our manufacturing process to accommodate this new design. Is it worth it just for this much improvement? And 20% improvement would probably be good enough, you know, but they might have a design that proves to be a better design, but it would cost so much to change all their, you know, infrastructure over in order to accommodate the new design that they don't think it's worth it. All right, so they would have to do this kind of an analysis to see whether or not they were going to go with that new design.
What's interesting too is that this newer one is a normal distribution, and the older design is just flat.
Yeah, you've got a, you know, if you get a normal distribution, that speaks to some level of consistency, you know. So. All right, now, looking at these percentages, another thing that we can consider, or we want to consider today, is the concept of percentiles, okay? And percentiles dealing with what's called a cumulative frequency graph. This is something that I've seen on a number of different mock exams and whatnot for the IB exams, the cumulative frequency graphs. So let's take a look at this. Again, we're taking a look at how data is spread. Later this week, we're going to get to telling how sets of data are related. But let's talk about a cumulative frequency graph. We're going to look at some data, look at how we can graph it, and how we can sketch the cumulative frequency graph, and then also how we can use that to interpret things. Okay? So, real quickly, I already constructed a cumulative frequency distribution table. Okay, basically, you have the frequencies, and we're just adding. Okay, So there were 8 in this first category, there were 3 more in the second, so cumulatively we have 11. Okay? The cumulative frequency tells us how many are at that level or lower. Okay? So now we can start actually graphing this with a cumulative frequency graph. The first thing we're going to do is kind of define our axes. All right? If we take a moment back here, when we are looking at percentiles and our axes on the graph, the percentiles tell us what percent of the data is at or below the particular value we're looking at. Okay? We've already dealt with this in terms of our quartiles, the 25, 50, and 75%. Those are percentiles. When we're constructing the graph, we need to construct the table like we already saw. Then we need to define our 2 axes. The y-axis is always going to be the cumulative frequency. Okay? The x-axis is going to be the data we're dealing with. And we usually end up having ranges of data because we've taken continuous data and classified it. And when you have those classes, you're going to plot the x-coordinate as the right-hand side of the range. Okay? So graph the point using the higher end of the range as the x-coordinate. Okay? So, getting back to our example was talking about, or was giving data for the women's marathon in the Olympics, and all of them were within the 2-hour range. So, when I start to draw my cumulative frequency, what I'm going to do is define my time as 2 hours and x minutes. Okay? 2 hours and x minutes. You can do it however you would like, but that's just how I'm going to choose to do mine. Now, you'll notice the first range starts at 26. So I'm just going to put 26 right here. Then it goes 26 to 28. So there's 28. Then it'll go 30, 32, 34, 36, 38, 40, 42, 46, 48, 50, 52, 54, 56. Now notice, in this data, they actually kind of broke one of the rules because they didn't divide all of the data ranges, all the classes, into equal widths, okay? We had 26 to 28, 28 to 30, 30 to 32, 32 to 34, 34 to 36, 36 to 38, 38 to 40, and then from 40 it jumped to 48, so 42, 44, 46, 48, 44, 46, 48, and then from 48 they went up to 56, so 50, 52, 54, oops, I missed a there, 56. Okay? So there you have it. You've got your x-axis labeled. Now when we're going to draw the graph, what I usually will start with is I know it's going to start here at 26.0. Then I'll go to the end, which is going to be your highest point. And the highest one is 69. So I'm going to make this 70. And then 69 is going to be right below it. Okay? And it's at 2 hours, 56 minutes, 69. Okay? So that's going to be my last point. Now I can simply graph the other points in relation to that. Okay? Now this is 70, so I'm going to go by tens, 10, 20, 30, 40, 50, oh, let me space those out a little bit better. 10, 20, 30, 40, 50, 60, 70, okay? So now, at 28 minutes, there were 8 people finished, so I'm putting my point here just underneath the 10, okay? Then after 30 minutes, there were a total of 11 people, so just above the 10, and you guys know how to plot points. But then by the end of the 32 range, I have 20 people done, so we have that. Then we went up to 31, so there's 31, okay, about right there. Using a straight edge might be helpful for you. Then we had 43, 10, 20, 30, 43, somewhere around there. Then 50, about right there. Then when we jump to, oh wait, I missed one, didn't I? Hang on. Scooch that over. Scooch that over. That should be over 38. That should be over 36. Okay. Then at 40, we were up at 55. Okay. Then finally at 48, we were at 63. Okay. And then we already got our last point. So now we simply connect the points. Okay? And there is our cumulative frequency graph. Okay? Your cumulative frequency graph should always be increasing. Okay? If it's not constantly increasing, you did something wrong. Okay? Because it's cumulative, so you can't like have a certain amount and then have fewer later on. Okay? Now let's look at interpreting this, and we're gonna finish up with this. Okay? If you need to get some more of this, you can see the PDF online, but I want to make sure we do the interpretation. Okay? First of all, let's think about our median finishing time. Okay? The median is which percentile? 50th percentile. Okay, so out of 69 runners, which runner is going to be the median?
The 2 hour 36.
Well, hang on. Don't. We're not using the table here.
69
Okay.
runners?
69 runners. So it'd be, which one is the median? The 35th, okay? So if we come up here, 10, 20, 35, here's 35. If we come straight across, and guys, this is how you would do this, all right? You're given a table, you'll look at it, you'll come straight across, and look straight down from there, and it's approximately 2 hours, 42 minutes, or 34 minutes, sorry.
Which is what they have.
2 hours, 34 minutes.
But
Okay.
you didn't need that right because you can just look at the graph. I mean, at the table.
Well, here's the deal. A lot of times when you're asked these kinds of questions, you're not going to have the table. You'll be given the graph. Okay? You're going to be given this graph. You're not going to have the table. You're going to have to use the graph to find out those answers. Now, we can use the table to confirm. Okay? The 31st person was finishing in the 232 to 234 range. So that fits. Okay? We can also use this to figure out how many competitors finished in less than 2 hours, 35 minutes. Okay? Well, here we have a time. Now notice 2 hours 35 minutes is is in this range. Okay, this is one thing that you can't get from the table. You're going to go straight up from 2 hours 35 minutes, see where it hits the graph, and then come straight across. And we could say approximately 40 of the runners were finished in 2 hours and 35 minutes. Right? Now, we can also then figure out what percentage of the competitors took more than 2 hours and 39 minutes to finish. Okay? So we'd come over here, 2 hours, 39 minutes. We'd go straight up from there. Then we'd come straight across. Okay? So that's about 55 people, right? That's approximately 55 people. So we had 14 out of the 69, right? 14 out of 69 took more than 2 hours and 39 minutes. Okay? So that's approximately how much, what percent? 35?
20.
Oh, wait, yeah. 20 what?
20.289.
Okay, so 20.3. Okay? And then finally, we can use this to approximate a time. Let's say, we were doing, multiple heats or something, okay? And only the top 20% were going to make the next heat, okay? Well, the top 20%, what's 20% of 69 people?
1 second.
About
13.8.
13.8, okay? So almost 14. So if we come here to 14, come straight across, we can say, hey, the time is about 2 hours, 31 minutes. Okay? Approximately 2 hours, 31 minutes. Okay? So, try using this. You got the practice. Okay? Draw them carefully. Answer questions. All right? See ya. Come ready tomorrow. We'll do the quiz first.